the other hand now, I have already explained why 1 over the gross inflation rate is the real return of money, right? Okay, real return of money. Okay, so one over in the other lecture notes, so you can see 1 over the gross inflation rate is the real return of money. So here, this is the asset pricing formula. Okay, you have the gross return. Okay, you have a gross return of the asset. In this case, it is money, and then you have this discounting and so on. So this is a no arbitrage condition in asset pricing theory. So, okay. You have seen this kind of thing in the capital accumulation case, okay, the real interest rate and so on. Okay, same idea. This is not an asset pricing formula. Whenever we see it, we want to point it out for you. So basically, the idea is that, okay, you treat this as the real rate of return of money. Okay, so if you have 1 unit of money in terms of goods, okay, in terms of goods, and you get that much of time t plus 1 goods back, and then it will worth that much of utility, time t plus 1 utility, and then you discount by 1 period. So everything will be in terms of time t utility. Okay, so this is the gross payoff of investing in 1 unit of real balance. Okay, and here you measure the amount of money by the amount of goods that we can buy. Let's say you don't measure 100, say your investment is $100, but you don't measure by $100, you measure by apples. So suppose apples is $2 for each apple. Then $100 means the amount of money that worth 50 apples. This is known as real balance. Okay? So you measure the amount of money by real goods, okay? In terms of real goods. So here, this is the gross payoff in time t utility. Okay, if you invest in 1 unit of real balance, and then the left-hand side, you have this. So you convert this 1 apple, right? So 1 apple worth for money versus 1 apple, 1 true apple. Okay, so this is the utility that you can get by consuming 1 true apple. But then, because the CIA constraint, you have this shadow price term here. So this is the distortion. Okay. Without it, if you don't have CIA constraint, this will be the no arbitrage condition. Okay. So you have a apple. Okay. So if you eat this apple, you get that much of time t utility right away. Okay. However, if you convert this 1 apple into the equivalent amount of cash, and then you will get that much of current utility back. Okay. So in the equilibrium without arbitrage, the 2 sides must be the same. Okay. However, with the CIA, you have a distortion here. So this lambda and other things to kind of understand the distortion. Okay, so then so those first order conditions and so on. So we will get rid of the dV, dNt, and so on. So then you can see the solution, right? So the solution of the consumer problem, and I call it CT star and this is a sequence, right? Okay. So M star is the solution, it's a sequence. CT star for t from 0, 1 up to infinity, and then t plus 1 star, and so on and so forth. Okay. Now MT plus 1, right? So 1 M0, right? Why I don't have M0? Because M0 must be exogenously given. Okay. Otherwise, the consumer problem is not well defined. Okay. Is the endowment, is the initial amount of money. Okay. Initial state cannot be a choice variable. And the same, you can see the same phenomenon. If you have capital accumulation, the K0 must be exogenously given, okay? Because otherwise, if I ask you to choose, if you can choose which person should be your father, then you choose Li Ka-shing, right? And everybody choose M0 to be infinity. Then the solution is unbounded, right? So it's not a well-defined maximization problem, right? Okay. So you don't have a choice of who will be your mom and dad. Okay. So it's an endowment, and then you have optimal choice of later on. Okay. Then how much time you want to study, how much you want to consume every period, and so on, right? Subject to your endowment. Right? So this initial M0 exogenous given, and because we want to ultimately look at the equilibrium, right? So that you want to set this initial money that the representative household has equals to the initial money stock printed by the government. Okay. Now, if they are not the same, then you can not have an equilibrium. You will end up with the time zero money supply not equal to money demand. Okay. But even though they are not equal, I think it probably doesn't matter too much. But anyway, just to keep things looks very nice. So just set the initial things to be the same. Okay. So you got these things, and here now. So this is the demand, right? So this is the demand side. So the solution of this thing is the optimal choice of the consumer, and so this is the demand side. So think of the solution of this is the demand for consumption, demand for money, then this lambda T star. Then you ultimately we want to, because we want general equilibrium, right? So our methodology is general equilibrium, supply side. So in this model, supply side very simple, right? So supply of goods, right? So the demand for goods equals to the total supply of goods, which is exogenously given, and then demand for money equals to supply of money for every time period. You can call it T plus 1. T plus 1 if you want to, doesn't matter, because it has to be for all T anyway. Okay. So you can see here the government, right? So once you have the money market clearing, right? So this empty star, if you put empty star here, empty star here, if you say the money market is clear, this is just say a cap M here, right? And then the government budget constraint will make these things zero at the equilibrium. Okay. So sometimes students are not that careful about demand and the equilibrium. Let's say when you solve this problem, you cannot impose equilibrium condition right away. You see, when you solve the consumer problem, you have to keep these terms. Okay? You cannot say, okay, at the equilibrium, because of the small MT is equal to cap MT, if the money market is clear, because the government budget constraint, this thing is zero, so this thing is drop, right? You cannot do that. Okay, so the demand may not satisfy, right? Okay, so that's why you want to keep all these things here when you solve the consumer problem. Okay? When you solve the consumer problem, you keep it there, and then the market equilibrium condition is imposed after you find the demand, right? So that's why you want to, so a more careful way is that first you write down all these first order conditions, those conditions that the demand will have to be satisfied, and then you write down very clearly the market equilibrium condition, and then once you impose it, then you can have the simplifications. So for example, so as you can see, you can also see the Warra's law right away, right? So here, Warra's law, so because it is consumer budget constraint here, and then you have the money market clearing, and then you have the goods market clearing. You actually don't need all three, okay? So because let's say you have money market clearing here, and then money market clearing, and then the government budget constraint, capital M follow these things. So this will be satisfied at the equilibrium, right, with money market clearing and government budget constraint. And then goods market clearing, CT star, so this thing 0, CT star automatically equal to E. So you don't need this one, all three together to determine. So just any two will be fine. So this is Warra's law in general equilibrium. So here, to get you understand a little bit better, I give you a concrete example so that you can see what this CT star, exactly what is CT star, what is MT plus 1 star, lambda T star, and so on. Now, it is CT star, it is easy, right? CT star must be ET, no problem, okay? But it's not clear what might be the equilibrium PT star, right? So we show you by construction. I can show you that. So here we need, in order to give you nice results, so because this is meant to be an example, okay? But this example is very instructive, okay, with a nice formula, okay? So this is an example. I want to give you a concrete example what this equilibrium, money equilibrium price should look like, okay? So suppose you have a economy with constant endowment every period, so every time you have the same amount of endowment, and then the government print money at a constant rate, okay? Let's say double the stock of money every time, right? You can have mil equals to 2, right? Double every time, so this is a very simple way. And then, so obviously this is trivial, right? So this is the competitive equilibrium consumptions, okay? And then money demand equals the money supply. But then because of these things, by repeated substitutions, MT plus 1 is equal to that. Repeated substitution, right? So M1 equals to mu times M0, and then M2 equals to mu squared times M0. Therefore, this is a formula, right? So here we can use this formula to compute MT plus 1 star for all T, right? Okay, explicit formula. And then how do you find these two, right? So you need to find these two to satisfy the Euler's equation, okay? This one, right? Okay. Rewrite it, okay? Just write it in a simpler way because of this U prime C thing is the same, okay? Rewriting, and then pi t is using Randy Wright's definition. The notation is this, and then the CIA constraint is this. So basically, you need to find a PT sequence that satisfies these conditions. Okay, and also this Kun-Tucker things, you want to make sure they are satisfied. So here, by construction, so here are so we can look at 3 cases. So basically, the case 1, case 2, you can construct it in a very nice way. So basically, the idea is to work backward. Okay, so and then try to get it correct. So for example, because of this CIA constraint, right? You want to make sure your PT will satisfy the CIA constraint, and obviously this thing is given, and then this thing is given. Just solve it, right? So you just solve because you only want inequality, right? So you can make it the same. Just use this equation to solve for PT. This will by construction satisfy. Okay, so this is the idea, and then now the algebra you can kind of take a look. So it actually works. Okay, by sort of working backward, it actually works. So basically, we can prove that if mu happens to be bigger than beta, you see this mu and beta, they're all parameters, right? Because mu is the growth rate of money set by the government. Beta is the discount factor, right? So basically, it says that if the growth rate of money is sufficiently large, okay, if government print money in a fast way, then there exists a unique equilibrium with this kind of features, with the price satisfy the CIA constraint. Okay, so CIA constraint binding. Then your lambda t calculate this way, and because your mu is bigger than beta, therefore this is strictly positive. So the CIA constraint is binding. So when the government prints money very fast, so basically this unique equilibrium tell you people will try to carry as little cash as possible. Okay, so the CIA constraint will be binding, just minimum, right? Just the minimum amount required by the CIA. Okay. And the inflation rate will be the same as the monetary growth rate. Okay. More difficult case, so this is not in Randy Wright, but I kind of prove it. So basically for mu equals to beta, okay, mu equals to beta, there will be infinitely many equilibria. Okay, so this thing I didn't copy from anywhere. I solved this problem by myself. So basically you can construct a continuum of equilibria. And you see what happened here is that the price level is not pinned down in the. So when your mu is equal to beta, you have many equilibria. All of them have the same inflation rate, which is equal to the monetary growth rate, but the price level, they are quite different. Okay, so you can imagine if you plot the time path of the price level, you have all these parallel lines. Okay, so the model cannot pin down the price level. It can pin down the inflation rate, right? So the rate of change of the price level. So basically, the construct this initial price level is slightly smaller than these things by any small epsilon, and then you can. So in all these equilibria, the CIA constraint is non-binding. Okay, non-binding, and therefore the lambda t will be 0. Okay, So the Lagrange multiplier or the CIA constraint is 0. So basically what happened is that when mu is equal to beta, the CIA constraint doesn't matter. Okay, people are indifferent between the constraint or no constraint. Okay, so you have this kind of results. So if they don't accumulate cash, or CIA binding or non-binding doesn't really matter to them. So case one also cover this case actually, because case one is mu bigger or equal to beta. So which means that mu equals to beta, you can have a equilibrium with CIA constraint binding, and you can also have infinitely many equilibria with CIA constraint non-binding. Okay, but I believe the utility level will be the same across all these equilibria. Okay, because the CIA constraint doesn't really hurt the consumer in this case. And then the case 3, I also proved it, and then it kind of so it just does not exist. So in Randy Wright, it try to say that it doesn't give you a proof. So it sort of say that a necessary condition for equilibrium is mu bigger or equal to beta. Okay, and then it sort of say that when mu is smaller than beta, then there's no equilibrium. So here in this example, we can prove it by contradiction. And this is, I guess, I'm not going to set this as PhD qualifying exam question here. Okay. But if you go to United States, this kind of thing. So we did that. Okay. Proof, all this proof. So if you don't have, let's say if you don't have a undergraduate course in real analysis or mathematical analysis proof, right, epsilon delta, you will have a hard time to pass qualifying exam in a top US econ program. Just the math will kill you, okay? Because they would like to set these kind of questions, proof, mathematical proof. But in Hong Kong, it's okay. We have an easy time in Hong Kong. Okay, so so this is just one example, and this example actually also has a certain pattern that you will see from time to time. So if you read Randy Wright's chapter, you will see whenever you have the monetary, let's say the money supply grow at a constant rate, and then you have this CIA constraint and so on. So most of the time you will find, not even most of the time, in all the cases in that chapter, you will see that the inflation rate has to be the same as the monetary growth rate. Okay? And then these conditions, the monetary growth rate has to be at least as large as the time preferences. So this is a kind of a central result, right? So this monetary growth rate. So the intuition, right? So here on mathematical, I think Randy Wright has a very nice kind of intuitive explanation. Why is there in this case when the monthly growth rate is smaller than beta, you don't have equilibrium, okay? Non-mathematical way. So basically, remember your beta is below 1, right? It's your discount factor, something like a 0.9, okay? And your mu is the growth rate, right? 1 plus the net rate. So then it means that the net rate is negative, okay? See this is 0.9, right? Suppose your discount factor 0.9, and then this is 0.7, right? Let's say the mu is 0.7, then it means that the net monetary growth rate is minus 0.3, right? Net growth rate minus 0.3, then it means that your money stock shrinks by 30% every period, right? So money stock shrinks by so you have less and less money in the economy, and you will have deflation, okay? Now, deflation means that money can buy more and more goods over time. So money is a good asset. It's a very good asset, right? So then in this case, the consumer will certainly want to accumulate money. So they will carry excess cash, right? So then your CIA constraint cannot be binding. Okay, so they will try to keep money. Okay, try not to consume that much. Try to keep money because your money can buy more and more goods in the future. But then, if you cut down your current consumption, you delay your consumption, there's a cost, right? Because your discount factor, right? Discount factor measure to what extent you hate to delay. So then this thing means that if this should happen, then it means that you prefer delay, right? Even though the cost for delayed consumption is high, but the rate of return of delayed consumption is even higher, okay? Because the money, the return of holding money, right? Return of holding money is very, very high. The rate of return is very high, higher than the utility or the cost that you hate delay. Now, if this is the case, then you could end up with violating, nobody want to consume, and then just try to keep delaying consumption forever, and so the equilibrium cannot exist. And along the same line, then you will understand why, when these two things are the same, you are indifferent, right? Okay, so when the inflation rate is the same as the way you discount future, then you are indifferent. You don't mind to carry excess cash, and also if you don't carry excess cash, that's fine. See, you're indifferent, right? So in this case, you're indifferent. So that's why in this we can construct an equilibrium like that. Whereas this case, when your mu is strictly bigger than beta, and then the rate of return of holding money is low, too low, right? Okay, so this 1/, because this, always keep in mind, mu, let's say it is the pi, right? 1/pi, right? So it's too low. So your rate of return of holding money is lower than the way you discount future, right? So therefore you don't want to hold money, right? So you just, but the CIA constraint is you have to, in any equilibrium, you have to satisfy it. So therefore you want to hold the minimum, just enough to satisfy the CIA constraint binding, right? So in this case. CIA constraint binding. So these are the economics, right? So economic intuition. So this is important. And here you also have a very simple implications. So when the CIA constraint is binding, right? So now this happens all the time, right? In the case of mu bigger than beta or mu equal to beta, right? So that's why in textbook or what, so usually people will just say CIA constraint binding, okay? And then they say in equilibrium, CIA constraint must be binding. Not true, technically. Not true, right? Technically, it is when the money growth rate is sufficiently large. But anyway, if the CIA constraint is binding, when people keep the minimum amount of cash required by the CIA, then you will have the quantity theory of money. Okay, so here, because this ET, let's say in the simplest case, your ET is constant. Therefore, the growth rate of money and the growth rate of P must be the same. Otherwise, you cannot keep these things constant, equal to the right-hand side, right? Because the right-hand side is constant number. So, and this is meant to hold for all P. So you double M, then your P has to double, right? So this is the neutrality of money, right? So if you double the stock of money, then your price level will also double, right? So the level shift, this is known as neutrality of money. Okay. And then now in this CIA model, actually this is a criticism of this CIA model. Now in the data, we can measure something called the velocity of money. Okay, so velocity of money, you take the ratio of nominal GDP and the amount of money. Okay, so nominal GDP. Okay, so in the data, you take nominal GDP, and then divided by, let's say, M2 or whatever, okay? And this is known as the velocity. So in the data, you can measure the velocity of monetary base, the velocity of M1, M2, M3, etc. Okay? So the concept is that, in this case, let's say PT times ET. PT times ET is the total expenditure, right? Total amount of transaction. Okay, total amount of transaction. Okay, and then divided by the amount of money. Okay, so let's say, for example, suppose the total amount of transaction is $100, and then suppose your money stock is $50. So you get this ratio to be 2, velocity to be 2. Then it means that for each dollar, we have to perform 2 transactions. Okay? So this is known as the velocity of money. Now here, in this case, because this is in the simple model, right? You have this equation. Therefore, PT ET divided by M must be 1, right? So velocity of money. So the money only change hands once in this economy. Now in the data, this is not true. And moreover, let's say suppose you don't care about 1, but the constant, let's say whatever number, but it is a constant, right? So but in the data it fluctuates. Okay? The velocity is not a constant in the data. Okay? So this is a criticism, right? So it's an unrealistic prediction from this model, from CIA model. Even more sophisticated version of the CIA model won't give you volatile velocity of money. And the so-called economic research, right? why I say economic research. So economic research means whenever you see a model that predicts something wrong with the data, you want to fix up the model, right? And so you say the model is wrong, so you want to add something to fix it, change the assumptions and so on and so forth. Right? Okay, so for those of you who would like to make a living by doing academic, so this is the kind of thing that you will do. Try to look at predictions from the existing theory and see if it is good or bad, and then try to fix up. Inflation rate, right? So in the real world, because output is not constant, right? And here these quantity equations would simple versions will predict that you convert this to growth rate. Okay, so easy way would be to take the ratio, right? So because you are working with the gross growth rate, so you take the ratio, then we just so you got this NT plus 1 equals to PT ET, right? Then you just write one more copy, and just shift backward or shift forward, doesn't really matter. And just keep it, and then you take the ratio. Okay, take the ratio, and then by definition, this is the gross growth rate of money, right? So this, and you assume, let's say maybe you can define it to be, if it is a constant, it will be mu, and then you take the ratio, right hand side you take the ratio, this is in gross inflation rate, and then you take the ratio, this is the output growth rate, okay? So in gross term, you will have something like this, and therefore in just rearranging terms, then you have the ratio. And then for net rates, because these things are all, net will be pi minus 1, right? You don't get the exact, but so you can write something like let's say maybe the net. Okay, so the net will be, so the growth. Let's say I write it this way. Okay, so you have this exact relationship, right, in terms of gross growth rate, and then this G thing is the net, is the corresponding net growth rate, which is what we normally call the inflation rate, the output growth rate, right? Because say the inflation rate is 5%, right? Okay, so normally we don't use 1.05, right? We use 5%. So 5% is the net rate. So if you take the log on both sides, and then use the approximations for these fractions, this is log 1 plus x, approximately x, okay? Use this approximation. So you will get, you take log on both sides, right? You take log, so you log, then this will be the log difference. So this is how you get the approximation. Okay. So in terms of net, right? So in the model, because in the model, those growth is in terms of gross growth rate. But in practice, we like to use net. Okay. So whenever you see a ratio in terms of net, it is difference. Right? Whenever you see a product in gross, then in terms of net, it is plus. Right? Okay. So yeah, let's take a break.
我不打了，不打去打。